Welcome to our 8th lecture in the atomic structure unit. Today we're going to talk about ground state electron configurations. Before we get into that, there's a subtopic that I delayed a little bit, and that is, I was going to say more, I told you I was going to tell you more about orbitals. Orbitals go into something, or come from something called the wave mechanical model of the atom. The idea was that a photon of light has a reality as a particle, but it also has a wave-like character to it. And because, depending on how you observe it, it can be observed behaving like a wave or behaving like a particle, we have this thing called the wave mechanical model of the atom. Now, because it behaves like a wave, it's really quite impossible to pinpoint the location of a wave. It's kind of like, think of it this way, a wave is like a particle that's been smeared. So when I talk about the location of a particle, I can only really talk about where it probably is. So when I talk about electrons, I need to say the following. When it comes to talking about where we find electrons, we need to talk about orbitals. And an orbital is a three-dimensional region where there's a 90% chance of finding a specific electron. So what isn't an orbital? Well, I think I said earlier that what an orbital isn't is not an orbit. Electrons are not traveling in a two-dimensional orbit, because in a two-dimensional orbit, you know where the electron is 100% of the time. We can't possibly say this in terms of actual electrons because of this wave nature, which makes it impossible to say exactly where the electron is. It might help you think of it this way. If I have these three-dimensional axes, an orbital can be thought to be a cloud. It's actually called an electron cloud, and it's very difficult to do, well, impossible to do in 2 dimensions, but even to suggest it in 2 dimensions. Think of this as being the cloud, the three-dimensional space, where there's a 90% chance of finding a specific electron. Now, that doesn't preclude the electron from being here, here, or there. We merely limit our search to this particular volume. Now, these orbitals, which are probable electron locations, are actually substructures. They make up what we call energy levels or shells. Now, a shell, I've drawn over here, a shell is not an orbit. A shell is an average amount of energy that a possible electron will have if it's found in that particular place, or if it's with probability found in that place. Now, we really talk about the first 4 energy levels. Notice the first energy level is closest to the nucleus, the second is farther out, the third farther out, and the fourth is furthest out of all. Now, it's an interesting relationship here. 1, 2, 3, 4. If n is the number of energy levels, then the maximum number of electrons that can be found in that energy level can be calculated using 2n squared. Now, you'll probably just memorize them, but I did want to show you that there is a strict mathematical relationship. Well, what's 1 squared? Well, 1 times 2 is 2. So the first energy level can have a maximum of 2 electrons. It doesn't have to have 2, but it can have a max of 2. 2 squared is 4 times 2 is 8. So in the second energy level, I can have a maximum of 8 electrons. I can have 1, 2, 3, 4, 5, 6, 7, or 8, or perhaps it's even empty. That's entirely possible. In the third energy level, well, sorry about that, 3 squared is 9 times 2 is 18. I can have a maximum of 18 electrons in the third energy level. Of course, I can have fewer. Of course, you can't have 19. No, no, no. The maximum is 18. And in the fourth energy level, well, 4 squared is 16 times 2 is 32. So in the fourth energy level, you can have a maximum of 32. And we don't talk about the fifth, sixth, or seventh because although they have theoretical maximums of electrons, you never reach them. Only the first, second, third, and fourth energy levels ever get filled up, and that only happens in the bigger atoms where you have a lot of electrons. Now, we've just talked about the maximum number of electrons that can be held in the first, second, third, and fourth. But we need to know the actual numbers of electrons in each and every level of an atom's electron configuration. So when I say the ground state electron configuration of an atom, this tells us the actual number of electrons that are in each energy level in the ground state, which I've written right there. Case in point, let's start off with a small atom, boron. Now, boron B, we go to our reference table. Now, we've dealt with a couple of different numbers so far. The atomic number of boron is 5. There's the atomic mass given for boron here. What you've seen before probably, but I didn't mention yet, are these hyphenated numbers down below. This is what we call the ground state electron configuration. The total number of electrons, well, in a neutral atom, it's equal to the number of protons, 5. And again, if this is the configuration of 2, 3, 2 plus 3, well, that's also where we get the total of 5 electrons. What this means is that in the first energy level, you have a total of 2 electrons, which happens to be the maximum. In the second energy level, you have a total of 3 electrons, far short of the 8. And how would that look schematically? Well, if this is the nucleus, and this is the first energy level, I could put 2 dots like so, representing 2 electrons. And then for these 3 dots, I'll place them like this. There is a reason I'm writing them this way, which I'll tell you about later. But notice, this and this are identical to each other. How about sodium? Well, we go to our reference table, and we see that sodium has, well, an atomic number of 11. If this is a neutral atom, then that means it also has to have 11 electrons. Of course, if you look at the electron configuration of 2, 8, 1, 2 plus 8 plus 1 is 11. Now, I can represent this 2 ways. I could write the 2 on the first energy level, the 8 on the second, and the 1 on the third. Or, of course, I could write in with dots, 2 dots in the first, 1, 2, 3, 4, 5, 6, 7, 8 in the second, and 1 in the third. Okay. Again, I do not have to have the maximum number. The first and second just happen to have the maximum number. The third energy level is far short of what it could be. Sodium in the ground state only has 1 electron there. A third example is vanadium. I go to table S and I see that vanadium is V. It's element number 23, 23 protons, atomic number 23. And it's neutral, so it has 23 electrons, and we see that it has electron configuration of 2, 8, 11, 2. There are 2 electrons in the first energy level, 8 in the second energy level, 11 in the third, and 2 in the fourth. Now, I do want to point out some that might puzzle you. For example, if we were to say Ta, that's tantalum, you see that when you look it up, it's hyphen 18, hyphen 32, hyphen 11, hyphen 2. That doesn't mean that it only has 4 energy levels. It's a compromise, meaning that in this space, I was not able to fit all of its numbers. So what they do, and they even noted here, it says, little asterisk, it says that when you have this situation with a blank and then a hyphen, 2-8 is implied. So if nothing is written, and or if you start with a hyphen, that means you should put a 2-8 in front of it. 2, 8, 18, 32, 11, 2. And again, these numbers are going to add up to the atomic number because, again, in a neutral atom, the number of protons are equal to the number of electrons. Okay. In our next lesson, number 9, we'll talk about excited states, meaning that we'll start with the ground state, and we're going to add energy and see how that affects the electron configuration. Okay. See you in the next lesson.